Today we're going to look at designing computer languages. Okay, so we're shifting, chink, over. Okay, so the metacircular evaluator is written in Scheme and it evaluates Scheme expressions. And if you're not already scratching your head by now, written in Scheme to evaluate Scheme. Where the heck does it ground out? How does this work? Okay. First of all, I'd just like to say that metacircular just means that it's written in the language in which it's going to be interpreting. And that's what metacircular means in this case. So before we really get into metacircular, what I want to talk a little bit is about Scheme. Now, you may say, Scheme, we've all been doing Scheme. And in fact, we can't. We have been. But you can think of each Scheme expression as a list. So if we had define A3, well, that could just be a list. Define A3. Parentheses, you mean the quoting? Oh, you mean these parentheses here? Let's just think about not evaluating right now. Let's just think about the expressions that we're writing. Okay, so we're just writing expressions, and we can think of these as lists. And in fact, Scheme thinks of these as lists. Yeah, this is why we're putting parentheses around everything. So define A to be 3, or we could write square 2, which is going to be the list, square 2. What I'd like to claim is that we've done lots of list processing. Do we have an agreement on that? We've done lots and lots of stuff with lists. Okay. What I'd like to claim that if we've done this amount of list processing, it's not trivial. But we could write a program that could just process these expressions as lists to do the right thing. What we could do is we could say, well, if it's a compound expression, it might just be a tagged list, where the beginning thing is telling us what to do. In this case, it's define, and here it's a procedure that we're going to need to apply. We could have a lambda expression. For some reason, I always misspell lambda. A lambda expression in which this at the beginning of our list will tell us that it is a lambda expression. Okay. So let's think about that for a moment. Let's talk about Scheme a little bit more. Scheme uses a read, eval, print loop. Which means that Scheme, and you guys have already had experience with this, will read in the expression we type into it. It'll evaluate it when we ask it to. It'll print out the answer, and it'll wait to read in the next one. So it's going through this loop. So we've got some reader that takes in characters that we type in. This is some input-output device, most likely our keyboard and our monitor. So the characters go into the reader, and the reader puts out list structure. So the reader figures out where the parentheses are. The reader is doing some of the matching for us. And that list structure is passed over to the Scheme evaluator. And this is what's going to evaluate our expressions that we're typing in. The Scheme evaluator needs something more than just what we're trying to evaluate. When we evaluate an expression, where are we evaluating it? Some environment, right? Well, if this is coming off the reader in our list structure, scheme is being passed right here, the global environment. So the schema value is using the global environment and the list structure we're typing in to produce some results. These results are going to go to the printer, which is not actually the laser printer, but something that's doing the printing to our input-output device, printing out to our terminal screen. The scheme evaluator is spitting out list structure to be used by the printer. And the printer sends characters back to our I/O device. So this is what scheme's doing. It's reading something in, it's evaluating it, it's printing it back out, and then it goes back and waits to read the next expression. Okay. Is this loop unfamiliar to anybody? Have you been on the computer for the last few weeks? Okay, now obviously this loop isn't always perfect, and the debugger can come in various places like here. But you can think of the evaluator as actually just spitting out list structure to the printer that causes it to print out information that we're entering the debugger. Okay, so we're just going through this loop.
What's the printer to reader? What's the printer to reader arrow?
Oh, this is the loop part of it. That we read, we evaluate, we print, we read, we evaluate, we print. So we go back for more. So that's our loop. So there's nothing being passed to the reader.
For its second.
Huh?
For its second pass.
Right, for its second pass. I mean, it's passing back to the reader perhaps a state variable saying, I'm ready for the next expression. You can think of it as saying, I'm ready. So when we pass the control back here, it's waiting to read, then the control passes here, and goes around in a circle like that for us. Okay. So that's what scheme's doing. I'd like to remind you guys of the rules of the environment model. The first rule is to evaluate a combination other than a special form. Evaluate the sub-expressions and then apply the value of the operator to the values of the operands. Anything unusual, unfamiliar there? You guys sort of familiar with this one? Hopefully. Please say you're familiar with this. Oh yeah? Oh yeah, we like this. Yes, may not like it, but you're familiar with it. Okay, the second rule is to apply a compound procedure evaluate the body of the procedure in a new environment. This is the create a new frame part. Yes? Maybe? Okay. To construct the environment. We're going to extend the current environment. Okay. With findings from variables to values. To evaluate a combination, we evaluate the sub-expressions and then apply the value of the operator to the value of the operands. To apply a compound procedure, we evaluate the body.
Is number 2 the step that you get, or how you turn your operator into the value of the operator? Is that the connection between 1 and 2?
So
one type of expression.
basically, 1 is when we figure out the values of all the sub-expressions. So we would have figured out that we had a compound procedure here. And here, to apply it, we're going to evaluate its body after we map its parameters. So this is when we create a new frame. We put the bindings in for the variables, and then we bound them to the values we passed in. And then we're going to evaluate the body of that in an environment. And it loops back.
And so that's the step that gets called to evaluate.
So basically, we evaluate the sub-expressions, and we say apply. Apply calls here if it's a compound expression. And if it's a compound procedure, rather, then we're going to evaluate the body. To evaluate the body, we go back up here. This makes what we call the eval-apply loop.
At the end of the first line is number 1. What's in the parentheses?
Except, other than special forms, SF. Our friends.
Can you turn the light on? So if you're not using
Okay. We have eval, and we have apply. In our system, these will be called MC eval and MC eval apply, rather, for metacircular. Metacircular eval, metacircular apply. The evaluator takes in an expression. It also takes in an environment, and it passes a procedure and arguments to MC apply, which then passes back to the evaluator the body of the procedure and what we're going to call an extended environment. Extended environment. We're going to have one variable in our system called the global environment. And this variable is going to point to a list of all the variables that are bound in our global environment. So we're going to have some representation for some primitive scheme procedures. This is some representation. It's actually going to be a list representation, but I don't want to draw that out completely right now. So we'll have some representation for primitive procedure plus, for the primitive procedure minus, some representation for the primitive procedure, whatever, divide. We might have some variables, some variable A bound to 3. So our global environment is going to be a list structure, and it's going to be a list of lists. Each of these things here in our environment are going to be lists. So our environment is going to be a list of lists. And this is where our bindings are going to be. So the global environment is the one that we can always see. Now, when we go to extend an environment, what we're going to do is make a list of our new environment and of the global environment. And this is how we're going to build those frames that we've been drawing in the environment model. This is how they're going to be represented inside of Scheme. Yes?
Notice that this is very similar to the tables that we saw yesterday, where we were using tables in the to create effectively bindings of values.
Johnston. Okay. So this is our new environment. This is environment 1. If we were to loop again, would create another environment on the outside of this. So you can think of this as all the subframes that we're creating in the environment model that we've been drawing in our diagrams. These can be represented inside Scheme. And in fact, you guys saw that these are all represented inside Scheme in problem set 7 when we asked you guys to trace the environments. Right? And you guys got to cut out and paste this large diagram. Large diagram. Save it, down with it, whatever you want to do with it, but you guys made the environments. Okay, so that's what the extended environment is going to be. So we're thinking of everything now in our language. I said how our expressions are going to be list structure, and our environment is going to be list structure. Okay. So we can write programs that operate on these list structures to interpret a language. Okay. The book talks about writing Scheme in Scheme. Okay. So let's actually think about levels here.
Can I ask a question
Sure.
about environments?
Yep.
If you have another new environment, is it possible that it would either point to the global environment or to new environment one?
It depends upon when we're evaluating it. Just like with the environment diagrams, some cases if we had the global environment here, there are cases where we might have one frame like this and then another frame like this. So if there were procedure objects here and here, this procedure object would see a list that represented these 3 frames. And this procedure object would only see a list that represented those 2. So it would have its own local list representing its current environments, what it can see. Just like we saw in the diagrams, represent exactly the same way. So when you're over here, you don't see those 2 frames over there.
Can that be demonstrated on this Watkins Wiener diagram here?
Well, what we would do is if we were creating a new environment, so this was point to the global environment. This would be, if I named my frames, E2, E3. This is going to be environment 1, environment 2, and then this is going to chain a list onto that with environment 3.
That environment 3 doesn't have 2 boxes, just 1.
Oh. Okay, so this would change. So the global environment, if it gets modified here, it'll be able to be seen in this chain here. If it gets modified by this one, it'll be able to be seen in this chain here. But anything happens in E3 or E2 can't be seen by E1. Similarly, anything in E1 can't be seen by E2 or E3. Yeah. So this is just going right back to the diagrams that we've been doing. Let me erase the read eval print loop. And I know John has been trying to tell you guys about levels. We should be thinking on different levels. And you guys did the pattern match. We talked to you guys about working on different levels. Okay, we need to think about 3 levels right now. Okay. The first level, this is where we're going to be interacting with the metacircular evaluator. This is going to be the commands we type in. So this is the commands we type to the metacircular evaluator, which I will evaluate as the MC eval. The second level, well, that's the metacircular evaluator. Which is made up of MC eval and MC apply. the third level is scheme. Okay. So we, typing in here, interact with 2, but we do not interact with 3. Okay. Effectively, 3 will be called because of what we're doing, but you can think of this maybe even as an abstraction barrier. Right? So we're typing in commands to MC_eval, and the metacircular evaluator is doing something for us. And it needs to call underlying scheme, but we're not typing in commands that skip over to scheme. They have to go through this second level in order to be evaluated. And then 2 gets to use 3. Okay, so we're typing in to the metacircular evaluator. It's typing into scheme. So just to contrast what we've been doing so far, well, we've only been in 2 levels. We have commands we type in, and then there's been scheme. So we're adding 1 additional level. That's what we're doing here, is we're adding another level. To distinguish, to make it easy for us, or easier, to see the difference between these levels, in the evaluator that we're using, in this code that you're going to get for the problem set, we've actually modified what the book is doing slightly. All commands in the version of scheme that we're typing in here will be prefaced by ADU:. We are now writing ADU scheme. So we will write, if we want define, it'll be ADU define. There is no space on either side of the colon, and it could have been a dash. The reason I started actually with a dash, the reason I changed it from a dash is because then I had ADU for minus, and it was ADU minus minus, which looked weird. So I changed it to a colon. But it's just a string that we're appending on front of the names to allow us to see when we're using the metacircular evaluator. So you have ADU define, we'll have ADU if, various things like that. Okay. So let's actually look at the system running a little bit. Since my projector's working, look at that. Yeah. Is this totally impossible for the back rows to see? You guys see this at all? You can. Cool. All right. So type in MC_eval loop and we evaluate. And we're going to get a command, meval input. Okay. This is another clue to us that we're working in the metacircular evaluator. Anything from the metacircular evaluator is going to say meval input when it's expecting input, and we'll say meval output when it's giving us something back. If we do bounce out to the debugger, we're out of the system, and then we're back in regular scheme. Okay, so we have not implemented MC debug. Okay, if the metacircular evaluator runs into a problem, we're out into the real debugger in the real scheme world, and you'll have to restart MC_eval loop once you quit out of the debugger. So what we can do here is I can add 2 numbers, which I will type ADU: plus 3, 2. To evaluate here, we're going to do Control-X, Control-E, just like we've been doing. Control-X, Control-E, and I get back that the meval value is 5. Notice I haven't tagged the numbers. We're not going to tag numbers. It's just not a good idea. So we're going to have 3, which evaluates to 3. We can define some variables in our environment. ADU define, A to be 3. Now, you can make a choice at this point. It's up to you guys on how you want to deal with the system. You can decide that you want to tag every single thing that you're defining with ADU:, and that's fine. So in that case, we would do define ADU_A to be 3. So now I can ask for the value of that variable, ADU3. Oh, sorry. And now we lose. So we try again. MC_eval loop. Okay. One other thing about when you guys are using this system. I found out last night that, well, you guys have already been finding this out. Sometimes Edwin gets into really weird states. You know, it never happens. Well, it does sometimes happen, and it happened a few times to me last night. So if you're starting to get behaviors where nothing's evaluating for you, you want to quit out of Edwin, restart everything, and hopefully You know, we will have exercised all the demons at that point. So let me try to redefine.
Do you use your global environment?
We do. There actually is a way for us to store it. It hasn't been implemented right now, but hopefully we'll get that implemented so we won't lose everything if it does crash out. So we're going to define ADUA to be 3, and we're going to try this again. ADUA giving us 3.
What exactly would happen if you didn't do an ADU define?
What would happen if we type in define x2?
I mean, I guess it'll just use the regular.
So it's not going to their own hand, but
Okay.
Because, why does this happen? It's actually giving me that I have an unbound variable x rather than that define is unbound.
it doesn't know it's a special form.
Doesn't know it's a special form.
Oh,
It's trying to evaluate the arguments, so it got to the x before it got to the define,
okay.
which gave us that error there.
Okay.
And the
Okay.
reason it doesn't go through to old school define is because we redefined the global environment.
Well, the reason it doesn't go through the old school define is what's going to happen. What we haven't looked at yet is the code for eval. And what the code for eval is going to be is like a big dispatch procedure. And what it's looking for is, you can think of it as looking for tag data. So aside from a variable, which is just going to look to evaluate, or a number, a symbol or a number, it's going to look to see if there's some tag on there. It's going to ask if there's a define tag, a lambda tag. Well, our define tag has ADU:define. Okay. So it's not going to know that that's a tag in our system.
You can't redefine define in the metacircular evaluator as define.
We could redefine define in the metacircular. We could make it be defined. And in fact, in the system in the book, it is defined. So let me show you guys eval and apply quickly. Then we'll look at the syntax and where we can define how things look. And this is going to be gone over in recitation, lecture tomorrow, recitation again. Yes, this isn't the only time you're going to see this. So this is, yeah, it's a big topic. Okay, so here's MC eval. So the first thing it's checking is if it's self-evaluating. Self-evaluating will check for number or symbol. If it is self-evaluating, then we just return the expression. So if it's a number, it self-evaluates to itself, the number. If it's symbol, then it'll evaluate to itself. Then we check to see if it's a variable, and if it is, we look up the variable value of the expression in the environment. We need to pass an environment. We need to know where we're looking up that variable. The next we check to see if it's quoted. If it's quoted, we'll return the text to the quotation, etc., through assignment, definition, if statements, lambdas, begin, cond, into applications. Okay, and these are in some sort of ascending order, because we want to check the simplest things first and then move up to the more complicated ones. Okay, so then you'll see that if we've got an application, we call MC apply. Okay, so that's what we're talking about there, is we're going to evaluate the sub-expressions, and then we're going to apply the first to the rest. So here we say MC apply if we've got an application. The MC eval of the operator, we're going to apply that to the list of values of the operands. List of values is a procedure that will take all of the operands and will figure them out one by one. It will evaluate them one by one. So right here, list of values, expressions, environment. If we have no operands, we return nil. Otherwise, we cons the result of MC evaling on the car of our list, the first operand, to the result of our recursive call for the list of values on the rest of them. This is going to evaluate all of our sub-expressions here. And apply, if we've got a primitive procedure, then we just apply primitive procedure. This is apply primitive procedure. This apply primitive procedure is actually bound to be the scheme apply. That's just scheme apply. And if we've got a compound procedure, then we need to do some other stuff. So this is eval, it's apply, and they'll call one another. And this is going to be circular. They're going to call one another until a point where the expressions get simple enough that it can just return the small parts. Sorry. I'm just watching myself track on the screen. Okay. All right, so we've got self-evaluating question mark, variable question mark, quoted question mark, assignment question mark, definition. Where are these? Well, they're all in the same file, and I'm going to search for the word syntax. This should be a few pages in for you guys. It starts off with following the procedures that define the syntax of our language. And there is a comment here, page 3 right here. And there's a comment here that we are prefacing all the usual scheme commands with ADU colon. Okay? This isn't the way it's done in the book. It's just going to make it a little bit easier for us to see it. Rather than writing typical scheme, we'll do the ADU scheme. So self-evaluating. This is just like a predicate test that we've had before, when we check to see if something was a book, or something was a soda, or something was null, or if something was a pair. We're just going to have these tests. Self-evaluating takes in an expression. If it's a number, we'll return true. If it's a string, we return true, otherwise return false. I think I was saying symbols before. I'm sorry. I should have been saying string. I apologize. For a variable, if we've got a variable, well, all we're looking to see there is if we have a symbol.
What is the variable question mark really looking for? How does it define a variable? Something that starts, if it starts with a letter, then it says it's a variable?
It has symbol work.
I mean,
It's using symbol question mark.
Symbol is actually, that's what I mean.
Right.
What does symbol question mark look, how does it, because this is not looking something up to see if it's in a symbol table somewhere.
No.
So,
I wish I had R4 with me to tell you exactly the thing, but basically it's looking to see if where did John go? John. John's gone. God. Symbol. Let's look up later. How embarrassing. Symbol is basically looking to see if it's a symbol, and I guess that doesn't mean anything, right? That's one of those self-referential definitions, right? It doesn't mean anything. We'll look up symbol later. Does somebody have R4 with them?
yeah.
I see Jeffrey flipping rapidly. So as Jeffrey flips, let me move the code down a little bit.
It returns true if the object is a symbol.
There you go. And you wonder why I don't know what the definition is. It returns true if it's a symbol. And it's a symbol if it is a symbol, therefore. It's tautology.
But it's a symbol in this underlying scheme.
No. This symbol question mark here is scheme.
Right.
Real, honest to God scheme.
So it's deciding in the scheme underneath whether something is a symbol from
Yes.
the scheme above.
Well,
From ADU scheme.
no, it's deciding, well, so we're typing in an expression. He's going to beat me. Oh my God! Good Lord! I think I'd rather use my finger.
Yeah, you got some AirPods.
No, no, I don't want to tear the screen. Goodness gracious. I appreciate it. Seems.
It just seems like, you know, you're asking the scheme underneath to say, is what I typed in 2 levels above a symbol in your language?
Well, in some sense, we are asking this middle level to deal with both. Because we're typing into the middle level, and the middle level is trying to convert this into the underlying level. So level 2 is dealing with both worlds. Okay, and when we type in a list, MC_eval is going to chug through this list and turn it over into stuff that the underlying stuff can evaluate. Let's go through some more, hopefully. Things that make more sense. This is the first one where we see anything about tagging. So I talked about how we can think of these lists, define A3 as a tagged list. So we have a question, quoted is going to be if we have a tagged list of an expression, and that tag would be ADU colon quote. Okay, so somebody had asked, can we write straight scheme? Can we use define instead of ADU define? All we'd need to do right here is remove that ADU colon. And just put quote, quote. So back quote, and then put quote. Okay, so this is where we could change the syntax of our language. So then the text of the quotation is the catter. So in fact, we could do weird things where we created all sorts of extra list structure or sort of weird ways of doing quotes. We could put an extra word in there. We could just change our selector, change the syntax. And it says what tag list does. It's going to check if we've got a pair. If it is, we take the car of it. Otherwise, we return false. Because if we don't have a pair, it can't be a tagged list. Right?
Single quote, quoting won't work, right?
It's not going to work. We shouldn't be using it here, no. right? Because we want to look for the symbol. We're reading each thing. We're reading each element as a symbol. So here's sort of maybe an answer to your question. So as we read through define A3, we're basically making a list of symbols, where the first symbol is define, the second symbol is A. We're effectively quoting each thing in the list that we're passing to level 1, that we're typing in. You can think of it as each one being quoted to the underlying representation. We're thinking of it just as symbols. And remember that quoting a number is just going to be the number itself, which is why it'll fall out okay up there for number expression. You can think of on level 1, when it goes to level 2, it's looking at that as a list of symbols.
So everything's a symbol that's not a string or a number?
Effectively, yeah. But if it's a compound expression, symbol will not be true.
Right.
So we have a pair, symbol will not be true, but anything else will be. So once we've pulled out the pieces, then we'll get to a point where we're just looking at variables. Because in fact, if we get to this level, then if we were looking up some variable, ADU square or something that we've written, then we'll go and apply it, but we need to find its value first. So we would get to a point where we broke out everything into its pieces, and then we applied it. Okay, we also have the ability to do set bang, which they call assignment. We check to see if we got a tag list with ADU : set bang. And if we have that, well, remember that set bang it said set bang variable value. So if we've got a list of 3 elements, the second, the variable is going to be the catter. The third, the expression that we want, assignment value, is going to be the catter. One thing actually while we're looking at this, I think I told you guys once in lecture that there were a maximum of 6. It's actually a maximum of 4. I think I told you guys the wrong number. If anybody did in the exam, we didn't take points off for it. Don't worry about it. Don't worry, it's okay. But when we saw that in the exam, I said, oh, we must have told them the wrong number. So I just wanted to tell you guys now, but you did not lose any points. It's okay. So definition. Well, it's going to be all the same thing. If we're looking for the definition of an expression, we look for a tag list that starts off with define. If we were looking for a lambda, we would look for a tag list that started with lambda. If we were looking for something else, we'd look here if. We look for a tag list that's starting with ADU if. Okay, because everything's a list, and you can think of it as a tag list. You can think of that first command as being the tag for us. And then we have the selectors that correspond. So the lambda parameters, that's the second element of the list, and the body is the returning of the list. Okay, there's no car of the coulter here. Why? For a lambda. We wrote a lambda expression.
The whole body, which is a list.
So the car of the coulter is this. It's going to be the list of X or the list XY or whatever we had. But if we took the car of the coulter, we'd only get that body's expression, which is why we need to take the coulter of the coulter so that we get the list of the entire body out. Okay, so that's why there we're doing a CDDR instead of a CADDR. Okay, and here we have a procedure, make lambda parameters body. And this is going to be used when we're trying to desugar defines. So we have define expressions, and we can do define in 2 ways. We've been doing it in 2 ways. One is that we can say define a variable to be some value, but we've also defined procedures, like square of x to be times xx. Well, remember, this is just sugars to define square lambda x times xx. In ADU scheme, in our metacircular evaluator, no, you can't type ADU scheme at the prompt, but you can start it up. If we were to say ADU : define, and then I could call it ADU square of x, ADU times xx. This would desugar into the lambda. So this make lambda is used when we have something that's sugared. The define procedure will break it apart for us. The define, what's going to happen in our metacircular evaluator if we have a define, so in this case it would be ADU define, is that we're going to check to see if the second element is a list or if it's a symbol. If it's just a symbol, then it's going to be this type of expression. If it's a list, then we know we're going to have some type of procedure definition there. We need to handle it differently.
Where's that split in the code where it does one or the other depending on what it finds?
Right here on definition value. So we check to see if it's a definition. And then right here, we say if we have a symbol as our second element, catter, we're going to return the CADDR, which is the third element of our list, our value. But if we don't, we must have a list, meaning that we need to make a lambda with the list of those values. That's a CDADR, because, let's draw this out. This is going to be the define. This is going to be the list square x, and this is going to be the list times x. And if I tag that ADU define, I would also need to tag that as ADU star. You can't use the underlying multiplication. We're going to call the primitive procedure for multiply in scheme, but we've tagged it with ADU star because we're representing it up in that second environment, the second level here. Okay, so I was drawing the box and pointer diagram so I could talk about why we're making a lambda the CDADR. So, which means we take the cdr, whack, car, whack, cdr, whack. This. Now, if we had had more parameters, this list would be extended out this way, say xy, and we would get all of that remaining list as a list. So that's what's going to return the list of the parameters, the comment formal parameters. And the body is going to be the cdr of the cdr. So I take the cdr again. This is going to point to the body.
And that includes the tag symbol, the ADU. ADU stars included in that clear.
Yeah. Okay. So that's where we decide on definition value which type of definition we have. That's how we decide, are we doing just a straight variable or are we doing a procedure? Do we need to desugar? If we need to desugar, this is what's happening here. We're making up a lambda. So we're basically consing the lambda tag, ADU lambda, onto our parameters and our body. So we're building up that procedure to return. So we desugared it in this step is what's happened. Questions? What if I decided I don't like to provide the sugared step? How would I change that? What if I decide we're just not going to use this anymore? If you want to define a procedure, you have to say define, ADU define, name, paren, ADU lambda, parameters, body. What if I decide there is no more sugaring going on in this world? What would I change over here? We could just return an error, right? We could just say error, sorry, this is not scheme, this is ADU scheme, and you can no longer do that. So, right, and so instead of doing this make lambda, and we would also need to change the definition variable too. Because here in definition variable, if it's a symbol, we return simply the catter, but if it is a list, then we return the car of the catter. There's the car of the catter, so this is going to be the cdr, the car, square. So we would also change that. Or maybe we wouldn't even want to bother returning an error. It's our language, and we're telling them We never told them they had a construct like that. Maybe we don't even need to error check for that. We don't have to. But if you're going to change scheme and you say this is very similar to scheme, you might actually want to do that. Questions so far? Yes?
All of the syntax is written in the scheme, not in ADU scheme. This is ADU scheme, but you wrote it in scheme. Is that right? Is that why you can use these parameters?
This is where our syntax is.
Okay.
You can think of this as a parser. You can think of this level as parsing out the same statements that you guys did in problem set 5. You know, if computer science doesn't work out, then basket weaving is a good option. Okay, so this is doing the same thing here. So just with our parser, we wrote it in scheme. And in that case, we were actually evaluating English-like sentences. In this case, we're evaluating scheme-like things, but it's not actually scheme. We're parsing it out here.
Is there a difference in the system between syntax and grammar? Where's the point at which it says it understands that it knows it's in parentheses, so that means something? Which part of the system understands that when you type something in parentheses, that means something?
Well, level 2 is expecting the parentheses. Level 2 is expecting lists of symbols or a single symbol.
But level 2 just gets a scheme list. It doesn't know that the parentheses were there, or does it?
That's how you make the list.
That's how you make the list, is by putting the parens around it.
It knows each discrete.
Or, so, I mean, if I wanted to use square brackets instead of parentheses, where is that?
But change the reader.
The reader is.
All right, so the reader's dealing with it for us. Because the reader, of course, conveniently enough, is in this back layer here. So if we look through the shadows, we see the reader is here. The scheme evaluator, that's what's actually running this. So we still have the same read print loop. The evaluator is just being, basically the evaluator is running a program that's simulating an evaluator. But it does ground out. Really, it's okay. The evaluator is running an evaluator to get scheme, but it's not infinite. It's not an infinite loop. There are just 3 levels. I actually think that's one of the toughest things to see. I think that's one of the hardest things when you're playing with this. At least it was for me when I took the class. I think it was for John. I think we figured out it was for Dimitri too. Yeah. So all of us had a real problem with that, which is in fact why we made the decision consciously to change it to ADU colon. Okay, because when we all took the class, they just said, here's scheme. It was run in scheme. And we're like, if you say so. So this is why we're changing it. And in fact, what we'll do in recitations and lectures is we'll show you how we can actually change the syntax of our language. We can use different words. Instead of lambda, we could use make procedure. We can use anything else.
Can we use the metacircular evaluator to write another evaluator?
Sure.
Like Jeff scheme or something?
Sure, if you wanted to do that. So then what you would do is you would write here in level 1.5, Jeff scheme. And that here would be commands that we typed into Jeff eval. So you could build on top of it if you wanted to. Okay. But it still grounds out. Yeah?
Or even better, you could use ADU scheme to write an evaluator, which would then run Jeff scheme.
Oh, okay. Okay. So I guess so if we want actually Jeff to be up here. Jeff scheme. This is still going to be commands and MC eval. And then conveniently enough, since we're in computer science, we can have level 0, which are commands to Jeff scheme. And we could go from there. Why? Because we can. Will we make you do that? No. We're not that mean. Yes, John.
If you wanted to have the ADU procedures as simply subsets, and so you could either use ADU colon defined for some functions or defined for others, you could do that simply by playing with the code in the definition diagram.
Sure. What we would do here is what we could do is we could have defined definition of expression to be or tag list quote ADU colon define and the other one would be tag list expression, quote, define. So then we could have it look like scheme or look like ADU scheme. Or we could define that to be bind variable, or I'm making a variable, or anything you wanted to call it, as long as you put it here. Right?
Could you run it so that in fact it would be a normal scheme for somebody who didn't know that there was no ADU scheme right on top of it?
Certainly. Yeah, we could make it exactly like scheme. And the book is trying to make it exactly like scheme. I just think that's harder to see when you're learning about the language, where it's grounding out. So if we change the names, it makes it a little bit easier to see where things are changing for us. And like I said before, we could also change, more than just doing these sort of cosmetic is the word I'm looking for. Cosmetic changes where we just change the names. We could really change the order. We could actually create a language that is infix instead of prefix. Right? So instead of writing +3 we could write 3 + 2. Okay, we could change our language. We could write to start doing assignments that look more like C. So instead of saying define variable value, we could say variable equals value. And we could start writing things like that. Yeah, so we can totally change the syntax of our language if we wanted to do so.
Could we, with this system and just changing these functions, have it handle 2 + 3 + 6? Can it understand, or is that back into the read loop? Things have to be processed differently.
Would need to recurse somehow to see if we had a plus in the second term, and then if we just ground it out after the next one, or if there was something in the fourth spot, in the sixth spot. So we need to do some sort of looping there on that type of expression to look for that. It's not incredible. You could do it. It's not trivial, but you could do it. It's not as easy as me just saying, sure, we could just say this is make procedure, or this is define instead of ADU define. But certainly you could do that if you wanted to do 2 + 3 + 4. We could write a language that would do that. Other questions? Yes?
When you did that list structure for
Yep.
the square, is that where you have square there, should that be ADU square?
It depends if I call it ADU square or not. There, I didn't. Okay, when we're defining a variable name, it doesn't really matter. You can choose when you're defining a variable name if you want to put ADU colon in front of it or not. Just remember which one you did. If you want to know every single variable and procedure name, and you want to tag everything with ADU colon, that's fine. It actually might be an easier way to see the whole system, but we don't need to. The only thing that needs to be tagged are define, if, con, the things that we're looking for as we parse down. But if we're defining a variable, we can call it anything. We can call it A, or we could call it ADUA. Okay, whichever one that you'd like to do.
The evaluator has its own global environment. Is that true or not?
Yeah, and it's called the global environment. And we can actually see where it's created. Yeah. Okay, so we define the global environment, which is all the way at the bottom, as setup environment. And you'll actually see in the procedure just below that our MC eval loop is what we use to run, is we're set banging the global environment to be the setup environment every time we reevaluate the loop, which is why we're losing any state. Let me scroll that up. Although, there we go. Okay, so this is, remember I said the question was asked if we bounce out into the debugger, do we have the state left? Well, every time we reset, we're refreshing the global environment, and we can make changes so that won't happen. And hopefully we can do that before the problem set goes out so that you guys won't be so frustrated having to type things in all the time. The global environment is setup environment. So let's go look for the procedure setup environment. Okay. Oops, too far. Okay. So the setup environment is we let the initial environment be an extending the environment with the names of the primitive procedures and the primitive objects. So we're going to make bindings from the names of our primitive procedures, which are going to be ADU plus, ADU minus, ADU times, ADU divide, ADU cons, ADU car, ADU cutter. And we could add other ones. I think that's all. Oh, ADU null. are the ones we have right now. And the objects are the corresponding primitive procedures in scheme: plus, times, minus, divide, cons, car, coulter, null. And those are extended onto the empty environment. When we first start out, we just put the primitive stuff in there, and we've got the empty environment to start out with. Now, I told you guys this is a list structure. These are abstractions to keep us from seeing that. But the empty environment is basically nil. And then we're basically going to put lists onto nil. And then we're going to define a variable called true in our environment that's going to be equal to true in the underlying scheme. So this is a symbol for our environment, and this is its value. And that's going to be set onto the initial environment. Then we have defined variable bang for false also. And then we return the initial environment back to the user. So we define the global environment to be what's returned from this procedure. So what's returned is what this initial environment is pointing to in that let frame. Okay, so then we return this as a global environment, and then we can look things up on it. We can change things in it using defined variable bang, which is basically set bang underneath it. Actually, set car bang or set coulter bang. Other questions? This is not the only time you're going to see this. We will have multiple days of this.
Could you actually write like C in this way?
Sure. It would be a C interpreter. It wouldn't be it wouldn't compile C. If, in this way in which you're writing it, we're interpreting a language, not compiling it. Yeah.
You have a problem with the curly braces.
Right. 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 But effectively C, but without curlies. Yes.
Is this more of an exercise so we can understand how things work, or would there actually be a reason you would want to build some kind of layer?
My instructor's favorite question. Why are we doing this?
I'm just wondering if you would. I mean, it looks very cool. I'm just wondering, like, if you would ever have a practical reason to do this.
If you were defining a new language, you might have a reason to do this. Actually, I believe a lot of C compilers are written in C, so there is some metacircularity there. You can think of this, I mean, in some sense we're writing just another type of parser here. We're doing that. But we could write a new language. We could write our own optimized scheme on top of it. Or probably not optimized, but our own favorite
Like
brand. Yeah.
To give to a user, you can
Right.
do this.
Right. You could write a simpler scheme if you wanted to give it to people. Excuse me, I don't hear.
Any kind of interactive program that would parse lists.
Sure. Right. Right.
Since this is built upon scheme, could it ever be any simpler than the original scheme? Because doesn't it have to refer back to the original scheme?
Well, it depends on what you mean by simpler. If you mean to the user, you might be able to change things so you simplify it, you never allow them to use syntactic sugar. And that might be a simplification because it'd never be a question for your user of, is this the sugared version, is this the desugared version?
But in terms of computer overhead, it's still going to take up...
I mean, it's still going to do the same thing in underlying scheme, right? Right. And in fact, it's probably going to take more overhead because we need to parse it, and then we actually need to do the usual stuff in scheme. Yes?
Or like with the things we've done with where we're reading input, like the symbolic differentiation and stuff, it seems like we're always having to quote things to send them in as an object that it can read and then sort of parse. But if we actually rewrote a whole interpreter to do that kind of thing, then we could make the syntax whatever we wanted. Right? Like it's not.
Right, you still need to tag it, right? I mean, and sometimes you'd need to tag things still, right? So when we had the generic operators, we had the ability to sort of abstract away for the user all this tagging going on. And if we were just to use the sort of simple system that we're using now, the user would somehow need to type in some tags, perhaps.
Or as long as it was consistent. I mean,
right, as long as there's some consistency, sure.
Or for the game, right? Yeah. We have to say ask whatever, and then we have to quote some keywords and leave names unquoted and stuff. But if we wrote a game evaluator,
right,
you'd have its own syntax, like ask
right,
or tell is the first word and the second word.
Exactly. Right, so we could do a game evaluator on top of scheme too. I mean, we've seen a lot of value.
It's like a different question. So what's actually the layer below scheme?
The layer below scheme is called magic. That's the magic level. Poof. We don't go there. Yes.
So the MIT interpreter, say it's written in scheme, it's somehow compiled, right?
Yeah, there's a compiled interpreter underneath it.
Otherwise,
Otherwise, it wouldn't ground out somehow, right? Because then you'd have an interpreter in scheme for the interpreter, for the interpreter, for the interpreter, for the
you
interpreter.
told me that's how it worked, I believe it.
If I told you there were hamsters in the back room, would you believe me on that too?
We already did it.
Okay.
So then
Well, there were, but we forgot to feed them. So now it's just Dimitri.
at some point, then Scheme does have the ability to actually access hardware. I mean,
Yes,
it's
it does ground out. Yes, it has to, right? It can't just keep interpreting. So it would actually, there'd be a compiled version at the bottom that actually just knows how to take it over. Yeah, I say magic, but it's not. There's going to be a compiled version. There is definitely something there that knows how to access the hardware, to evaluate the scheme, and put it into machine instructions. There is something there for that.
It would be interesting without spending too much time on it, just to have a little kind of list of how you get down to, right down to storing, you know, through ASCII to storing binary, etc., from scheme down to the most basic level. I mean, it'd be interesting.
This sounds like a great thing to do in recitation. Notice the sneer. Yeah, we're going to do some compilation in register machines. We're going to talk about this anyway.
And I will give a quick overview this afternoon.
After he beats me up in the office. Other questions? Yes.
One thing that I was reading in the book that seemed entirely too. At this part, I can almost buy the circularity here.
We've almost sold you on it. I have a bridge, too.
But the conditionals, where they say that the evaluator, if you get an if statement, it feeds it to this eval if. Well, the eval if is defined by an if.
Right, because that's all, it's just the same thing. It's just like we're using, you know, define or let in level 2 that's bounding out to scheme. We can use if in our eval if that's going down to scheme, because we're at this layer here. So you have the ADU if down here, and then eval if can use the if from here. We can't get it from here.
If from where?
Which uses this magic layer, the compiled layer that goes to the machine instructions.
So, if it uses a magic if in the
Magic if, yes, the magic if.
why bother with that intermediary? Why don't we just feed it directly to the magic if?
Well, because we are in effect doing that through our scheme, right? Because that's what we've been using so far as scheme. We actually haven't talked about how to write machine code.
Okay, so
Because scheme is basically on top of machine code, right? There aren't little define commands, you know, little define words running through the bits in yours. You're getting zeros and ones. So there's definitely something that's taking level 3 down to what our machine can understand.
So this eval in here in the book is not the true scheme evaluator. It doesn't truly go through an eval if, which will break it down.
The eval there is for the eval of a metacircular evaluator, which is why you would typically write meval or MC eval instead of just eval.
It's with ADU tagged on the front of all the things we're defining. Makes it a lot easier to understand.
Good. Maybe you guys all should get it, unlike all of your instructors.
Defining if in terms of if, yeah.
Right. It's really hard. I think it's hard to see when you've got if in terms of if, where the heck it is. So if you've got ADU if in terms of if, it's a little bit easier. Or, you know, instead of if, we could change it to maybe, or possibly we'll do this. Or, you know, we could change the whole, some sort of non-deterministic if, random if. We could do something like that in our language. So we could write anything on top of it. Okay, we're basically simulating scheme, and the reason that we're simulating scheme in this upper level is because you guys know scheme. We're not going to write a completely new computer language right now, because while some of you have seen other languages, there's not a language in which all of you have seen it, and we don't want to go off on another couple of weeks teaching you a new language so we can show you how to interpret in scheme, which is why the example is to do scheme in this metacircular evaluator. Yeah. We had a few more weeks.
The other thing I noticed reading is that this is done entirely without higher order procedures, and there's a footnote that alludes to the fact that you could, in other languages that don't permit higher order procedures, implement them. And that by creating this within that other language, and that struck me as really cool.
It's
That's all I
cool.
have to say about that.
It's the magic layer. Any other questions?